much for Tim's introduction, and thank you all for being here. Very appreciate your time. So today I want to talk about a new work on physics of learning, and I'd like to start with the foundation of learning structure. So the start of this project comes from that I want, like as many of you do, like we want to understand intelligence. So I'm developing under this one hypothesis that intelligence. So I also don't want to overtake the time, so I also make sure that I'm on time. So I'll talk as much as I could. So we're under this hypothesis that I think species, agencies like us, we developed intelligence because we are under evolution. We have the need to learn to survive in a finite amount of time. So that's the hypothesis I was having. So I thought efficient learning is key for intelligence to arise. So we have a lot of learning paradigms that exist in the machine learning communities, from reinforcement learning, unsupervised learning, to regressions and generative modeling, and they are all powered by deep architectures. And some of the work is trying to address is that whether there's a universal principle that underlying all of those learning paradigms and whether we can find them. So the spark of inspiration comes from the physics, where I was wondering why light travels in a straight line. Apparently, it is not random. It was optimizing a certain objective function called principle of least time. That's by the Bellman's principle. So in particular, it says a ray of light travels from point A to point B. It chooses a path along which the time is the least. By least, it means stationarity. Actually true, but stationarity. So in particular, if we look at the objective, the left-hand side is time. We're looking at distance divided by velocity, and we're traveling from point A to point B. So say in a normal circumstances, it would be a minimization process. If you put a minimization process in a 3D geometric space, you can actually compute the path of your traveling, and that is the straight line. That's how physicists compute how light travels. So the inspiration comes is that I think the universe is rather a very elaborate system. It was rather efficient. I don't know how, but if we think about design an efficient learning system, we are having an information processing engine, that's a physical system. The physical system takes along the information space. It works along the information space. It takes samples we take and they absorb information. And then the goal of an efficient learning is that we try to find a minimum path that reaches the generalization errors in the shortest time. Well, I haven't discussed what I mean by time and what I mean by the minimum path, but that's where the inspiration comes. So apparently such law is not only applies to light optics, it also applies to Newtonian mechanics and many mechanics that people have in the physics. It was generally being called as principle-based action. So as an example from the particle dynamics in the left-hand side, if we throw a free particle in the space and it will take the parabola shape like the left-hand side, that's what we observe in life. And that's the imagined motion on the right-hand side. And if you're a physicist, you would wonder why a particle would take that shape instead of the left or right-hand side shape. It turns out they are actually also minimizing the objective function or finding the stationary point. The objective function they are finding is the particular where the integral over the time t1 to t2 over the kinetic energy of the motion minus the potential energy of the motion. So half mv squared minus the potential energy. And in physics, when you are looking for stationary paths, the true path is the one for which that integral is least. So that is something that was done in physics. And the inspiration comes is that when we design a learning system, what are the objective function we're trying to minimizing? And once we minimize to it, what's the result coming out of it? So in the new work that we're doing in the physics of learning, we're making a bold statement and we do some demonstration. We're saying the learning tool follows the laws of physics. In particular, we demonstrate it follows the principle of least action that we did before, that we showed before. And our contribution is that with respect to each physics objective function, we give a corresponding learning Lagrangian. And what we do is we look for the stationary solutions, just like physics does, because through finding the stationary solutions, the physics tells us what's the optimal path we're traveling because of the efficiency statement. And my research asks the question, what is the stationary solution path when it goes down with the optimization of the objective function? So to get started a bit is that first, the physics moves in a geometric space or physical space, while a learning system is moving in an information space. So in a sense, I need to understand what's the kinematic movement in the information space. So in a in information cases, when we take each sample S1, S2, S2, ST, if we define the position as the Shannon's and the information that we get, which is the Shannon's entropy log P, the velocity was being defined is the instantaneous change with respect to position. Surprisingly or non-surprisingly, it is the next token prediction. So if you do the calculation. And then you can also have the acceleration process similarly. And what we're doing is the velocity curve is the in-context learning loss. And similar for the pre-trained learning, when we take batches of data, and what we move is in the generalization error space once we see the batch of data, and the reduction is the rate of the generalization, that's the test loss curve. So in the physics perspective, when we are plotting loss curves, we're actually plotting the velocity of the learning curves. So the question is, what is the acceleration? Well, it's rather simple. It's just the acceleration. It's just the derivative of that. You see it, and that's the right-hand side. That's the left-hand side is in-context learning loss, and the right-hand side is the acceleration. We can see it is a deceleration process. Well, okay, so it's a deceleration process. I guess the meaning is that when an agency learns, the first sample will give you much more information. You learn much more, then you go for the lower samples. And in particular, because the probability is lower bounded, in general, when you are decreasing lower bounded monotone convergence, you are supposed to converge to a minimum. But of course, this needs more mathematical theory to do it. So you are in a learning, you have an infinite, and you are decelerating. Okay, but that was just preparing for the more exciting things coming later, is that in the end, we try to optimize objective functions. We now understand what does movement in information space means. So the objective function that I'd like to demonstrate is the first is the principal of least time. And the third one is the stationary action, which was governed by the Lagrangian dynamics. And the second row is the Hamiltonian system, which is the Legendre transform of Lagrangian, which means the solution achieving the Hamiltonian system is the same as the Lagrangian system. And so the three in physics are can be interchanged. So they are kind of like governing the similar principle, but affected in two different matters. Like one slide, the other is mechanicals. So here I started with Fermat's principle first in my investigation. So as I said previously, I was saying efficient learning is walking along the information space, such as takes the least time. By time, it is like when we design a learning system, we take numbers, the samples in, and suppose the information content of each sample is approximately similar towards each other. Then least time means the sample size. And it is still an open investigation to quantify time when the information content for samples are varying. But so far, let's assume that. And what the Fermat's principle is saying, it just simply say, we observe information one each. Once I see my generalization error hit a threshold delta, and I say I stop. And the point is I want to minimization, controlling my data such that it can learn the fastest. So that I mean by the efficient learning. Well, that was active learning. It was unsurprising. But I can do a dilute over here. I guess this don't need to be dilute over there. So I think, well, that is active learning, but we have this small problem, which is that we are unknown for the generalization error in general. So if we want to compute that, we have to assume a parametric model, and I start to say, oh, what's my generalization error, and how should I choose my data? This is just a demonstration of a very linear regression. You can do that. And I will skip the details for the time constraints. What you will get is that you can actually, under very parametric cases, you can compute the generalization error. And that means you can select data such that when the generalization error hits, you say, if you want, say, 1.5 sigma square, that's what you should select in your data. But what's a little bit demonstration is that whether when you're selecting your data, whether it travels as a straight path as your light. And the question, the answer is not actually in your information traveling, because when you're greedily selecting your data in this particular toy example, you are actually needing that to each selection of your data, you need to be 1 over PIP, but because you're only selecting singleton data, you can never match the rank difference. So you have to select blocks of P data. That means when you're performing efficient learning, planning is very important to continuously learn in the most efficient way. But that's just a small demonstration. I want to do a more general case. Actually, in fact, what I want to showcase is that the reinforcement learning is optimizing this one, and we'll go down to its stationary action. The Bellman optimality equation is the stationary solution that comes out. So what that means is that when learning efficient learning, so essentially looking for stationary solution gives you learning algorithms that people are currently using. I just want to demonstrate that. So for the reinforcement learning, if we look at it, we want to maximize the formats principle. We have the previous difficulty, which is that we do not know the generalization error, but reinforcement learning was substituting with a reward. So we don't have to know, we just assume the environment will give us a reward. But now the problem comes with the minimization part, with the data path. Previously, it's the active data selection, but the reinforcement learning was substitute that too. It was optimizing action subject to constraints. So once you are optimizing action, you are actually effectively selecting your data path, your state path, subject to your dynamical constraints. So you are able to rewrite the whole objective function into the right-hand side, where you have the objective with the terminal reward, continues over the reward functions, subject to transitional dynamics, which is the next state transition, with state and action, etc. So I just want to show, I just want to show how the Bellman optimality comes out and how it was the connection to a Hamiltonian system. So if you write down the Lagrangian and you are looking for stationary solutions, which means the partial derivative need to all be 0, that means all the red boxes need to be 0. And the initial conditions is 0. Initial state does not vary, so that part is 0. What you need to do is all the other 3 boxes is 0. And that gives you equalities here. Inequalities with the boundary condition is your terminal reward. So if you set your lambda k as the gradient of the value function, you substitute into the second equation, what comes out is the value function of the reward, because that's taking the gradient of the state, taking the partial gradient of the state. This is taking the gradient of the state at your next state with respect to partial derivative state. So that's exactly this part. And now you also need the maximization of the action, and that gives you exactly the Bellman optimality equation. So what that means is that I started with my problem is that I have a Lagrangian. I want to search. I do not know how to optimize. Now the reinforcement learning replaced the generalization error with reward function. Now I optimize this. The stationary solution is Bellman optimality. So in reinforcement learning, when we're optimizing Bellman optimality equations, we're actually looking for stationary solutions in the Lagrangians. And so that's the Hamiltonian system, but I still do not know the reward function because they are substituting the reward function with respect to Lagrangian. So in my next, in the work, we hypothesized what we mean in supervised learning by Lagrangians, and what it comes out is the stationary solution MLE, and they have to follow Adam-like behaviors, and they have some predictable theories in terms of optimizations. So this is the overview of the work. Yeah, happy to take the questions.